All right. Hi, everybody. Thanks for coming. So our speaker today is Marius Müller, who is now just moved to Freiburg University, and he will talk about the Willmore Flow of Tori of Revolution. Please go ahead.
Yeah, thank you. And thanks to all the organizers for the opportunity to speak here. And also thanks for the effort to keep scientific exchange alive. I really appreciate it. Well, today is my talk is going to be about the Willmore Flow of Tori of Revolution. And we will see what all of this is in a minute. So let me go ahead and first define the Willmore flow, or talk a little bit about the Willmore flow. And after that, I will talk a little bit about what Tori of Revolution have to do with it. Well, the Willmore flow is the gradient flow of the Willmore energy. So it's the L2 gradient flow of a geometric energy, namely this energy here, which you get if you take an immersion and you take its mean curvature and you integrate it over a whole surface, and this defines your Willmore energy. For now, we are just looking at immersions going from a surface sigma to R3, and sigma is supposed to be a compact two-dimensional manifold without boundary. We will also call it from time to time closed manifold, and yeah, our image lies in R to the 3, so this is just the situation we're in. And now we look at the mean curvature of F, which is now for our convention supposed to be the trace of the second fundamental form. So there's no 1/2 in the definition of the mean curvature. It just sometimes works better this way arithmetically. All right, the Willmore energy is sort of interesting because it measures how much a surface bends. So it is sort of a bending energy, and there are other mathematical properties which are also of interest. Namely, for example, it has many invariances: translation, rotation, scaling is an invariant, and also Möbius inversions, at least if the center of inversion does not lie on the image of the immersion, so does not lie on the immersed surface, then also Möbius inversions are invariants of this functional, and this makes it very interesting from a variational standpoint. And yeah, one can also, so since we will be considering the L2 gradient flow, we should actually compute the L2 gradient once, even though it won't matter too much throughout the talk. So the L2 gradient of this Willmore energy is the Laplacian of the mean curvature plus a nonlinearity, again involving curvature terms. So it's a fourth order equation, and it's nonlinear. And we call critical points, so points where or immersions such that the gradient vanishes, we call them Willmore immersions. Yeah. So don't worry too much about this nonlinearity or anything. It will not be very relevant in the talk. All right. So now, what is the Willmore flow? The Willmore flow is the L2 gradient flow of the Willmore energy, and we impose that it's a smooth, that we always have a smooth evolution by this gradient flow in the direction of the negative gradient. And first of all, of course, one should ask whether such evolution exists, but short-time existence is somewhat standard. Kuvert and Schätzle, in their first article, it's basically the first one of a series of many articles about the Willmore flow, basically gave an estimate for the maximal existence time, which is already very interesting. So this forms sort of the basis of the existence theory for the Willmore flow. What is not clear up to now is whether the Willmore flow generally exists for all times, and under which conditions it converges. This is recent research, but yeah, there are also some partial results, none. Especially there's a situation where much is none, namely if the sigma, so the manifold that prescribes the topology of the immersions you consider, is the sphere. So we are talking about spherical immersions there, which are immersions that go from the sphere to R3. And if you start the Willmore flow with such a spherical immersion, that also satisfies that the Willmore energy of this initial immersion is less or equal than 8 pi, then the Willmore flow exists for all times and converges to the round sphere. So this is the global minimizer, the round sphere is the global minimizer among spherical immersions, and this will be the limit of this evolution, which is very interesting, why this threshold of 8 pi comes up here. For this convergence result, the threshold of 8 pi is actually sharp. So just slightly above the level of 8 pi, one can find singular evolutions. So evolutions by Willmore flow that are non-convergent. We don't know whether they are the singularity occurs in finite or infinite time. So the question after long time existence is still not known for those singular evolutions. But what is known about the singular evolutions is that they do not converge. And yeah, this I will show you in a second the singular evolutions, how they can look like. So this is an example for an evolution of the Willmore flow, which develops a singularity. Yeah, this is a singular example, and it's made in the way that you take a curve, right, and you revolve it around a certain axis. So this large axis is a revolution axis for the surface, and then you revolve and you get a surface, and if you take this as initial datum, the Willmore flow will not converge. And one can actually examine numerically what happens along the Willmore flow to this surface. And what will happen is that this loop here, right? You have this loop here in the middle of the surface. It will basically contract to a single point, and this will be the singularity, or this will sort of be the reason for a singularity. Yeah, and actually what it does in the end, it converges to two spheres that are just next to each other, with a point around which the singularity occurs. And the point that joins the two spheres is basically the point where this contracted loop goes to. And this makes it, yeah, this makes this behavior singular. Yeah, so this is an example, and it was rigorously proved by Simon Blatt that it does not, that the Willmore flow does not converge if you start with this initial datum. All right, so far we have talked about spherical immersions, or immersions from the sphere to R3. And now we are looking at another genus. We are looking at tori. So immersions that have the topology of S1 times S1. And we want to consider even more, so we prescribe that the tori have a revolution symmetry. So we prescribe that there has to, the torus of revolution has to be a torus where that revolves a curve around a certain axis. So you take a closed curve in the upper half plane, and it needs to be closed, otherwise it won't be a torus, and it has to be in the upper half plane entirely. And then you revolve it, and what you get is a torus, definitely, because the immersion I can now, which I wrote down here, goes from S1 times S1 to R3. and this will define a torus of revolution. So I will always abbreviate this torus of revolution as S of gamma. So if you have a closed curve in the upper half plane, then you can form S of gamma and think of it as being the surface that revolves gamma around the x-axis. Okay, so this will be my notation for that. This is a torus of revolution, and now one can again look at the Willmore energy and look at tori of revolution that have a special sort of Willmore energy. And what is known is, for example, that the global minimizer among tori of revolution, and actually also among all tori, is the Clifford torus. So the Clifford torus is simply arises from revolving a circle with certain radii and a certain height around the x-axis, and so this will be the global minimizer among all tori, and so it's sort of the nicest donut you can construct, and the ratio of height and radius plays an important role for the energy. So yeah, this is the global minimizer. And so one would expect this, for example, as the limit of the gradient flow under certain conditions. All right. How is this relevant for the flow? Well, it's relevant for the flow since the flow preserves this revolution symmetry. So if you start the Willmore flow with a torus of revolution, then for all times, the surface you're gonna get will also be a torus of revolution. So the revolution symmetry is preserved, and this is actually this is what our approach is based on. All right. So now I can state the main result. So we have looked at the Willmore flow, started with tori of revolution, and we are interested in the asymptotic behavior and long time existence. And what we proved is that if we start the flow with a torus of revolution of Willmore energy less or equal to 8 pi, then this Willmore evolution exists for all times and converges in a sense which I won't really go into, but just note that it's up to reparameterizations. It converges up to reparameterizations to the Clifford torus or some translated, rescaled, or rotated image of it. Those can always occur since they are invariants of the functional. So they basically, this immersion converges smoothly to the global minimizer up to reparameterizations. All right, so this is the main theorem, and just note that this threshold which we have here again, so the Willmore energy, we also require the initial energy to be smaller or equal to 8 pi. It is the same as for spherical immersions. So this was sort of surprising, or maybe also not. There are multiple reasons, and maybe later I will have time to explain why this 8 pi bound is sort of interesting, or why it could be sort of universal. In our case, it's also optimal. So for us, we were also able to prove the optimality of this energy bound. Namely, just slightly above the level of 8 pi, you can find non-convergent evolutions of tori, or of tori of revolution, we should better say. So you can also find tori that become singular, and not just the example that I showed you 2 slides ago, which is a spherical example. You can also find a whole class of singular examples for tori of revolution. and they will all look like such a 8-type curve, such a figure 8. Though this is actually a curve which I plotted here that has Willmore energy of 8 pi plus 0.01 or something, so not much more than 8 pi, and its evolution will be singular. And basically, what is also interesting is that the reason for this evolution to be singular is sort of the same. It will also happen that a loop of this 8 will close along the flow. So along the flow, you will observe that this lower loop of the 8 actually, so the lower part, will be contracted to a single point. Yeah, so this is also the singularity that happens there. We will also later go into that. But for the next few slides, I want to convince you of this convergence theorem first, so of the positive result that if you start below 8 pi, then you're going to converge to the Clifford torus, so to the global minimizer. I should mention, and I totally forgot in the first slide I intended to, this is joint work with my PhD advisor Anna Dall'Acqua, Adrian Spener, both from Ulm, and Reiner Schätzle. So yeah, I've forgotten about that, sorry. And yeah, so let me now tell you a little bit about the proof of the convergence theorem, or just about the approach. Okay, so what was our idea? The first idea one can have is, well, you take now this torus of revolution, and then you get a Willmore evolution starting with this torus that preserves the revolution symmetry. So at each time you have you have this revolution symmetry. So at each time your immersion will be just a curve gamma of t revolved around the x-axis. So it will have this structure. And with this, you reduce the dimension of the flow, right? You can now look at the evolution of gamma of t only. So you just have to look at the profile curves, gamma of t. I will also call them profile curves a couple of times. I just have to look at how they evolve in order to be able to determine how the whole surface evolves. Okay, that's the idea. And now I regard the evolution by Willmore flow as evolution of this gamma of t as an evolution of smooth curves, smooth closed curves in H2. What is H2? Well, basically H2 is just the upper half plane, but there's more to this story, since we will look at this evolution, at this curve evolution, in a special geometry, and it will be the hyperbolic geometry. And this is why I don't write the upper half plane here anymore. I will always write H2 from now on. H2, I will now justify why it sort of makes sense to look at the evolution as an evolution in hyperbolic geometry, or why this hyperbolic geometry naturally comes up. And for this, I start with defining what I mean by hyperbolic geometry. Well, the hyperbolic half plane is the upper half plane equipped with or endowed with another metric. Namely, you take this metric G, which has a scaling factor 1 over y squared. And then you have just the identity. So you have you scale the Euclidean metric with this, and then you get the hyperbolic half plane. There are other models to describe the hyperbolic geometry, but we will look at this one now. And why is this hyperbolic geometry the right geometry to look at this flow? Because there is a useful connection, namely to another well-known curvature energy, which is Euler's elastic energy in the hyperbolic plane. This connection was observed, it is sort of classical. It was observed by Lange and Singer in 1984. So the Willmore energy of the torus of revolution is actually given by pi/2, so just a constant factor, times the integral over this profile curve, over this gamma, over the curvature squared. Yeah, this is this is a useful relation between Euler's elastic energy and the Willmore energy of Tori of revolution. So those energies just differ by a factor. And this is really interesting because now you know that this energy, this integral gamma kappa squared ds, is controlled along the flow, basically because the Willmore energy is also controlled along the flow. This is a property of the gradient flow. So this energy will always be decreasing along the flow. And this is maybe something where one can, what one can use to obtain further control. So this is interesting. I should mention here at this point that the L2 gradients of this Willmore energy and the L2 gradient of this integral kappa square energy, which I from now on will call Euler's elastic energy, the L2 gradients do not coincide, basically because the L2 spaces do not coincide. You take L2 always with respect to the surface measure, and it's not the same as the arc length measure of the curve. So even though those energies just differ by a factor, their L2 gradient flows will not. And in an earlier project, we looked at the L2 gradient flow of this elastic energy, and some things did carry over to this Willmore flow, but for some things we had to work more. And there's also a couple of reasons why one has to work more. Because, I mean, now I could hopefully convince you that this hyperbolic geometry is sort of an interesting geometry to consider for this flow, but maybe it's not the whole truth, because of what is here. There's an obstruction to just look at the flow in hyperbolic geometry, because basically scaling in the hyperbolic geometry is an isometry. So if you compute any hyperbolic quantity along the flow, if you compute how it evolves, everything you can say is only up to scaling. Yeah, you won't be, so the hyperbolic geometry will not be able to monitor the scaling that the flow performs, basically. So it could be that the flow shrinks something very heavily, and the hyperbolic geometry will not see it because scaling is an isometry. So scaling doesn't make much of a difference. And this is an obstruction to deal with this Willmore flow just in the hyperbolic geometry, because one definitely has to exclude that the surface is scaled up or scaled down. The Willmore flow could theoretically do that, so we need some scaling control. And for the scaling control, one needs to work a little bit more. We had to leave the hyperbolic world again to basically obtain this control. And what comes into play here is basically an interplay between the revolution symmetry and the curvature concentration criterion, which is sort of a blow-up criterion that has been known for a long time for the Willmore flow and was also derived by Couvert and Schätzle. One has to understand how this revolution symmetry interacts with this criterion. I will briefly, I will later tell you what this criterion precisely is, but basically, this can be used to obtain the scaling control. This criterion characterizes the behavior of the Willmore flow at a singular time, and you can actually use this revolution symmetry to say that at the singular time or at a hypothetically singular time, not so much can happen, because you can basically, well, I should basically tell you now what happens, because otherwise I feel like it is very imprecise. So let me be more precise about this point. If you have a Willmore evolution up to a maximal time t, which satisfies that t is less than infinity, so let's say it exists for only finite time, then we need a singularity at the singular time, and the singularity will be in the form of evil points. This is what the curvature concentration criterion says. So the curvature concentration criterion says that you get evil points, and the points are evil in the sense that the second fundamental form is very large around this point. So around this point, you have a very large second fundamental form. Think of this closing loop phenomenon, right? We talked about these examples where the singularity was that a loop closes, and this closing loop happens with a lot of curvature. And so this evil point will be the point where the loop contracts to. Sort of, there will be a lot of curvature, and this is a criterion for a singularity. So you have actually, this is the only thing that must occur at a singularity. You get these evil points where the curvature is very large, or where the second fundamental form is very large. Well, this happens at a singularity, but now look, we have this revolution symmetry also. So we do not just have evil points. Since the situation is revolution symmetric, every revolution of the evil point will just be equally evil, because now the second fundamental form is also revolution symmetric. So it gets large at every point where on an evil circle, basically. So the evil circle is what you get if you revolve an evil point about the x-axis, and along all these points, the second fundamental form is very large. Yeah, I mean, I didn't exactly tell you what very large is, but believe me, an evil circle of large radius will cause a very huge Willmore energy. So you can never get an evil circle of large radius. This is simply too evil to have finite Willmore energy. Yeah, this is the whole idea. So you have this interplay between the revolution symmetry and the curvature concentration criterion by getting this evil circle whose radius you can control, sort of. And this gives you scaling control. This is actually what is what is the whole point. You can get scaling control by this interplay between revolution symmetry and curvature concentration criterion. All right, so this is why we get the scaling control, and this is also why maybe it still makes sense to look at the flow in hyperbolic geometry. And indeed, we could prove the following convergence criterion. So the following convergence criterion is, if the hyperbolic length, it's natural now that you have a hyperbolic quantity here, if the hyperbolic length of the curve, I will define that in a minute, stays bounded along the flow, then the evolution of this flow exists for all times and converges smoothly. So suppose you have a Willmore evolution, and you know that the profile curves the length of those profile curves stays bounded for all times, then you know that this evolution exists for all times and converges smoothly. All right, this is the convergence criterion. And now, let me just mention the hyperbolic length is actually given by this integral. So you have this factor of gamma true, which basically it makes it basically scaling invariant. So it's now scaling invariant, and you this is the hyperbolic length. If this quantity of the profile curve stays bounded, then the Willmore flow converges. Okay, in some other talks, I give a proof of that, but here I decided not to, because I wanted to elaborate a little more on the question, how do we ensure that evolutions have bounded hyperbolic lengths? Because this criterion is pretty useless if no evolution whatsoever had bounded hyperbolic lengths. But actually, you can control that for some evolutions, and I will tell you a little bit about in which situations you can do that in the rest of the talk. Okay, so now's a good time to take a breath. Now we will sort of look at this hyperbolic geometry more. All right, so we need to control this hyperbolic length. So we need to control this quantity LH of gamma for curves gamma along the Willmore flow. And what is the first thing one would try maybe is to control this length by the Willmore energy of the surface of revolution, because this Willmore energy here, this is controlled along the flow. So if you look at the flow, the Willmore energy is controlled by a certain constant because it's decreasing. And if you can prove such an estimate here, which I wrote down in red, then you could also prove that the hyperbolic length is bounded. So it would be really desirable to have such a bound. The problem is this is not true. Unfortunately, this is one can actually show that it's not true, but there's a partially positive answer which we're going to discuss now. Namely, so if you fix an epsilon positive, then for all closed curves in hyperbolic space, whose elastic energy, so integral kappa squared ds, is smaller than 16 minus epsilon, you can prove that the quotient of elastic energy and length is bounded from below by a positive constant, but only below this energy threshold of 16 minus epsilon. This 16 here, which shows up, is actually sharp. You cannot prove such a bound below any energy of 16. So why do we take now the elastic energy? What does this have to do with all that? Well, now we know that the length is controlled by the elastic energy. If we rearrange this inequality, then it says the length is smaller than 1 over c times the elastic energy. And now, what one can do, the idea of proof I will explain later. What one can do now is use the connection between the elastic energy and the Willmore energy again, which I told you some slides ago. Maybe it's been too long ago, but this elastic energy and the Willmore energy only differ by a factor. And this means that if the Willmore energy is now below 8 pi minus epsilon, this means that the elastic energy is below 16 minus epsilon. And then you can control the length by the elastic energy. And this means you can control the length by the Willmore energy, because again, they differ by a factor. So this is actually, this one actually can prove, and one makes very much use of this correspondence. And now it explains a little bit more why this 16 is so important here. Because 16 in the world of curves equals 8 pi in the world of Willmore surfaces, or in the world of surfaces. All right. So now if you start the flow with Willmore energy below 8 pi, then you can bound the hyperbolic length along the flow. And then our convergence criterion, which we had slides ago, says that the evolution will converge. Okay. Is that the theorem? Unfortunately, this is not the main theorem, because now we claimed that the limit is now the Clifford torus and not just any Willmore torus of revolution. So far, we only know that we have a convergent evolution, and the limit could now be any Willmore torus of revolution. But actually, the limit will be the Clifford torus. And in order to show that, we have to exclude all other Willmore tori of revolution. First of all, one could, of course, ask, are there other Willmore tori of revolution? And the answer is yes. Here they are, or just a couple of them. There are infinitely many Willmore tori of revolution, actually. So those are their profile curves. They look pretty so this is how they look in the hyperbolic half plane. If you know about the Poincare disk, there they look more or less nicer, because this first one here looks like a sort of childishly drawn flower with 3 leaves. This looks like a flower with 5 leaves. This looks like a flower with 7 leaves, and so further and so forth. Yeah, and we have obtained these explicit parametrizations of them, and you will see why. We are actually not really the first ones who worried about how they might look like. So this is how you can look at the Willmore tori of revolution. Now we can prove, if you have a Willmore torus of revolution whose energy is less or equal to 8 pi, so less or equal to the threshold which we imposed, then this torus of revolution must be the Clifford torus. This is something that we can prove, and basically one can or a way to basically explain that is that all the other Willmore tori, so all of these guys, have a self-intersection. And there is a famous Liao inequality that says that all surfaces that have a self-intersection will have Willmore energy of 8 pi or above. Actually, there is a slight struggle with the equality case here, but this also works out. Yeah, we will be able to prove the theorem for less or equal to 8 pi. Then you have the Clifford torus. And the main tool is now that you have these explicit parametrizations of Euler's elasticae, and so of the critical points of the Willmore energy or of the elastic energy. Now it's all the same. This is the equation that a critical point of this energy has to satisfy. It's also a 4th order ODE now, and you can integrate it pretty explicitly. Sometimes it's not fun, but it's very interesting, and it can be done very explicitly. I should, so now we have proved the main theorem. For the rest of the talk, I will go a little bit into how I can construct, or how we can construct the singular evolutions, because this shows the sharpness of the main theorem, or the sharpness of the threshold of 8 pi. So here I claim that if we have a closed curve such that if you integrate now over the Euclidean curvature and not over the hyperbolic curvature, And if you get a 0 there, if you start the flow with such a curve, then the evolution is not the Willmore evolution of the surface of revolution associated to this gamma naught is not convergent. This one can show. And what is the reason? Basically, the reason is that there's no possible limit available, because what one can show is that there exists no curve, no closed curve that is a critical point of the Willmore energy, so that satisfies Euler's Elastica equation, and that also satisfies that this total curvature, that this integral is 0. And this integral turns actually out to be a flow invariant. So it will actually happen that that if there is a limit, it would have to be a curve with total curvature 0 and also a Willmore immersion, so also a solution of this equation here. All right, so this is the reason for non-convergence, and maybe I should tell you how the Willmore Tori of Revolution, what is their total curvature. So this quantity T is called the total curvature, and this quantity T looks like so. So for this flower with 3 leaves, its total curvature is 2. For the flower with 3 leaves, its total curvature is 3, and so further and so forth. And again, one needs a very explicit parametrization of those to be able to actually compute that. This involves quite a lot of elliptic functions, and was part of this earlier project. Basically, we had to do the same thing already for the elastic flow, or for the flow of the Elastica energy. All right. What one needs to show now, I claimed that just slightly above the threshold of 8 pi, there are non-convergent evolutions. And indeed, just slightly above the threshold of 8 pi, you can find curves that have total curvature 0. Yeah, you can find those curves, and they will look like this 8-type example that I gave you some slides ago. And yeah, so this just slightly above 8 pi, you get those singular evolutions, and you get a whole class of them. All right, so in the rest of the talk, let's look at how the singularity forms, or what happens to the singular evolution. We know now that this 8 must be singular since it has a total curvature of 0, and so there must be a singularity. And how will it look like? Well, first, for a small time, the flow will look very innocent. It will preserve this 8 structure, sort of. And then there will be a singularity, and I already foreshadowed that the singularity will be that this loop contracts to a single point. And what one can also show, this is again a consequence of the curvature concentration criterion that I gave to you. Yeah, this is also not really rigorous, because in infinite time it's not a consequence of this, so one has to be careful with that. But what one can show is that the singular behavior of the Willmore flow must always occur at the revolution axis. So if you have this evil points, those evil points must always be close to the revolution axis. So you will have this loop contracting, and it will happen at the x-axis. All right. So at this, just at the singular time, you will have a very small loop below here at the revolution axis. And then you can also sort of characterize, even though this is still, there's still some uncertainty here, that the limit will now be the inverted catenoid. So this limit profile you will observe here at the singularity. So the loop will give you the singularity with a lot of curvature. And what you will obtain here is the inverted catenoid. So you take a catenoid curve and you apply the Möbius inversion on it. And then what you get is, again, a surface of revolution looking like so. So at least you can apply some Möbius inversion. Of course, someone will also break the revolution symmetry, but if you apply one that keeps the revolution symmetry, the profile you will get looks like so. And what one would very much like to understand is whether the singularity occurs in finite or infinite time. But yeah, unfortunately, we do not really know that now. So it would be very interesting to find out more about that. Well, and so this is what happens to the singular example. And yeah, there's still something to be discovered. So now this is an if time allows section, the next 2 slides. And actually, since time does not really allow, I will not talk about conformally constrained Willmore minimizers, which is an application. This flow has numerous applications, but we don't have time for that today. Anyway, thank you for your attention.
Thank you very much. Are there questions?